Good morning, Physics 30. Hope you're ready to rock, ready to get some physics done. So what we are going to do today is we are going to be starting at the practical application of the uses of light. So we're going to be looking at reflection and refraction today, and then we will, after that, be going on to the uses of lenses and mirrors. So very, very practical applications of EMR. So today we're only going to talk very, very briefly about reflection, just kind of what it is. And then we'll be looking more at reflection when we start talking about mirrors and curved mirrors, that kind of thing. And then we're going to be looking at refraction, so how light bends as it moves through different objects. So as its speed changes when it starts moving between different media. So we're going to be breaking this lesson into a couple different videos. First, we're just going to look at the basics of reflection and refraction, and then we'll go over a y equals mx plus b question, your favorite. Come on, you guys love putting data into y equals mx plus b. It's your favorite. And then we are going to have a second video where we will talk about critical angles. All right. Ready to rock? Ready to roll? Awesome. All right. So, ladies and gentlemen, our law of reflection says that our angle of incidence is going to equal the angle of reflection. Now, the law of reflection is both going to work with particle theory and with wave theory of light. So it's going to fit with both theories. Okay. And our angle of incidence, this is essentially our initial angle, our entry angle, essentially. So these angles are always going to be measured from the normal line. So that's super important. And we are going to be having that's essentially our common reference. It always is going to be the same with mirrors as your normal line. So think back to physics 20 when we talked about normal force. Well, normal force is always perpendicular to the surface. Well, so is our normal line. So your normal line is 90 degrees to the surface. So here, this line here is our normal line. Now, we'll put a star here, our angle of incidence is going to equal the angle of reflection. So if I'm going to have a beam of light entering here and it's going to hit this surface, it will then reflect up like that. So the theta that is going to be here with the normal, my theta of incidence, is going to be the same as theta 2. Please keep in mind, this is not to scale. Artwork is not great. Okay, and this is our surface. Okay, so the value of our theta of incidence is going to equal our theta of reflection. So if theta 1 is 20 degrees, theta 2 is 20 degrees, and it's always in comparison to the normal. So we'll be coming back to talk more about reflection later when we start looking at mirrors. So this is just kind of our introduction to reflection, and we'll talk more about it later. Okay, so our big topic for today is refraction. So refraction is super interesting, and it changes how light moves through different objects, how light bends as it goes from one medium to another. So always a fun story with this one. You guys know how much I love my stories. Back in 2011, my family and I were hunting in Texas, and one of the things we did with our guide was bow fishing. Now, bow fishing is illegal in Alberta, but it's legal in Texas. A lot of things are legal in Texas that are not legal in Alberta when it comes to hunting and fishing. It's just nuts. So with bow fishing, the best way to do so in Texas is you get a flat bottom boat at night with flood lamps, and you shine light on the fish. All of these things are completely illegal in Alberta. Flat bottom boats are fine, but not fishing at night with flood lamps and bow fishing. So when we're bow fishing in Texas, it's ridiculously hard because you got these bows that have string on them, special arrowheads that are going to design to stick to the fish. So we always have to aim like really far under the fish. Like you're not even looking at the fish. You're aiming so far under it if you even want to hit the fish, because the refraction of the light is so significant that the fish actually looks like it's higher up than it is. So you have to aim farther, way underneath it. And so it was quite difficult. So you're firing fish and bow arrows into the water with your bow and then shooting fish. It was nuts. So, but where you aim when bow fishing, pure evidence of refraction. So kind of fun. Bow fishing illegal in Alberta, legal in Texas. We were in Texas when we were bow fishing. Okay, so back to the math and not my goofy stories. So refraction, it's when our wave is going to change direction when it goes from one medium of another. Now, this guy, ladies and gentlemen, isn't only changing direction, it's also when they're going to be changing their speed as well. Okay. Now, this guy supports wave theory of EMR. Okay. It's also called Snell's law. So the law of refraction is also called Snell's law. And it's how EMR is going to bend. So how it is going to do so, how the wavelength, how the speed are all going to change when it moves from one medium to another. Okay. So ladies and gentlemen, the speed of EMR is constant in the same medium, but it's going to change if it goes into different media. Okay, so here's your equation here. It's one big old equation here. In your data sheet, though, it's broken down into two. Okay, so you guys see those equations right there? So you have the top one right there, and then you have the equation underneath it. So these two guys are where you're going to find that equation. Okay, so with this, notice how we have 1, 2, 3 equal signs. That means you can pick and choose which items you need to compare. So we can compare the signs of the thetas. We compare your index of refraction. You can compare sign and speed. You can compare wavelength and speed. You can compare index of refraction and speed. Like, it doesn't matter. Pick two entities, and those are the ones you're going to compare. Okay. So with this one, theta is our angle measured from the normal. So theta is always measured from the normal. Okay, so that is super important. We always have a reference. It won't be said what your reference is because it's always from the normal. Okay. Now, n is our index of refraction. So we'll talk a bit more about that in a moment. Lambda is our wavelength in meters. And v, it's your speed of the EMR. Most of the time it's going to be light, and it'll be in meters per second. So ladies and gentlemen, in air, it is going to be 3 times 10 to the power of 8 meters per second. But in the other media, it is not necessarily going to be. Okay. Now, 1 and 2 subscripts are going to annotate different media. So, for example, 1 could be air, 2 could be water. 1 could be, molasses, and then 2 could be water. Who knows? Oil. So, but just keep the numbers the same. So another key piece here, ladies and gentlemen, I would definitely say lesson subtle hint and on test and all that if we are having tests, but we're not having tests, so I can't do that now. There's no frequency in Snell's law. No frequency. So what this is telling us is that the frequency of the EMR is going to stay the same. Frequency doesn't change. But that means when we look at our equation, V equals F lambda, if frequency stays the same, that means both of these guys are going to have to change. So this guy will stay the same, but these guys will change. Both of them will. Sounds good? Okay. So when light moves from one media to the next, All right. So, ladies and gentlemen, we have our index of refraction. So this is n. So this is a fairly new value that we have looked at. It's essentially a way to compare the optical density of different materials. So how hard it is for light to move through them. So a really, really dense material is going to be really hard for light to move through. Whereas a material that is very, I guess not dense, will be hard or easier for light to move through. So just how easily light can move through it. Now, a low index of refraction, so air, where air is 1, ladies and gentlemen, please keep that value in mind. The N for air is 1, okay? And it's easy enough for air to travel through it. Now, diamond, air is harder to travel through. So the N is going to be 2.42, and that's not a value you need to memorize. So what you can do is you can imagine running on pavement. Compare that to running in water. Now, when it's a lot harder for you to run through water, can you do it? Absolutely, you can. But it's harder. So if you start running on pavement and then you start immediately running in water, assuming the transition is simple, and you yourself are going to slow down. It's harder for you to move through that. Whereas if you are going to be running from water, and which is harder to run through, and then you go on to air and to running on pavement, you're going to speed up. It's a lot easier. So the higher the index of refraction, the harder it is for you to move through, for light to move through. It has no units, and because it is just a comparison of a value, so it is a unitless number. And n in a vacuum is also 1. Okay, so let's look at a couple of brief examples here, ladies and gentlemen. One other thing I forgot to write down. Let's go back here. Okay, so we talked about it, but we didn't write it down. Okay, so when we are going to enter a medium, so when light enters a medium where n is going to be lower than the n of which the medium is, the EMR is going to speed up. If the EMR is going to enter a material with a higher n, it is going to slow down. So exactly like that idea with running through water and pavement. So if you go from pavement to water right away, you're going to slow down because it's harder to move through. Whereas when you're running from water and then onto pavement, you're going to speed up because it's easier. Sounds good? All right. Okay. So let's look at our first practice problem here. So a beam of red light has a wavelength of 700 nanometers and is traveling through water, which has an index of refraction of 1.33. The beam of light leaves the water and travels into a piece of flint glass with an index of refraction of 1.75. Determine the wavelength of the light when it is in the flint glass and compare the frequency. All right, so let's look at A. Now, as always, ladies and gentlemen, drawing stuff out is going to make your life infinitely easier. Okay, so there's our surface, so that's where the object is going to be changing. Here's one medium, here's the other medium, and here our dotted line is the normal. So I'm going to switch colors now so we can look at our beam of light. You know what? This is going to bother me. I drew our background in red, and then I can't draw the red light in red. That would drive me crazy. So we're going to draw our media and materials in blue. There we go. So here's our normal. Here is where what I'm going to call our surface. This is where the water to the flint glass is going to change. Now we can draw a red light. This is going to make me feel way better here. So we are going to be having a ray of light that is going to be entering from the water into our flint glass. Now, note we have in water, ladies and gentlemen, we have our index of refraction of 1.33. We have also been given a wavelength of our light here. So our lambda is 700 nanometers. Now, I am going to leave my units. Oh, hi, Freya. Freya's joining us. We're going to leave our red light in nanometers here, ladies and gentlemen, because when we look at our equation, the units are going to cancel out. So that means we're going to be left with our units in nanometers. So this is one of those units in, units out type formulas. So as long as you keep your units consistent, you can use whatever units are available. Okay, so now notice we're going to be going into our flint glass, which is going to have an index of refraction of 1.75. I'm just going to actually move that over so I've got more room to draw my ray of light here. So N2 is our 1.75. Now that means that the ray is going to be slowing down. It's going from a less difficult material to move through to something that's more difficult to move through. So when it slows down, it's going to bend. Oh man, this is it's really hard to draw this stuff so you guys can see what's happening. It's going to bend towards the normal here. Okay, it's slowing down. It's going to bend towards that normal. And we have been asked to determine the wavelength of the light. So we've been asked to determine lambda number 2 here. So ladies and gentlemen, we are going to use our Snell's law. And when you look at your data sheet, you're going to see that you can pick any of the sets you need. I am going to pick my N2 over N1, and I'm going to equate that to lambda 1 over lambda 2. Now, you don't need any of the other info. You only pick the 2 values that you need. Don't pick any of the other ones. We don't have any of the other data. So only pick those 2 entities that you need. So I am trying to find lambda 2. So I'm going to rearrange my equation here. I'm going to multiply by lambda 2 to bring it to the top to make it easier. And now, once lambda 2 is there, okay, I am now going to multiply out my N1 over N2. And those guys will cancel. And I'm going to be left with my lambda 2 is going to be lambda 1 N1 over N2. Okay. So once I've rearranged that equation, I can now go and put my numbers in. So my lambda 1, once again, I'm going to leave my units in nanometers. So what it just means, I'm actually going to put my units in here so we can do some unit analysis here. Yoink. There we go. And now my n values are unitless. So 1.33. And we're going to divide that by the 1.75. Notice there are no units. Oh, hi, Freya. Freya's bringing me a ball to show me because she's a good girl. Right, Freya? Okay. Excuse me. Throw the ball to the dog. Go get it. Okay. So these values are unitless. There's no units to cancel out. The only units we are left with here are nanometers. So when we write out our lambda 2, it means that it is going to be in nanometers. So plonk your numbers into your calculator and you're going to get 532 nanometers. All right, so ladies and gentlemen, there is your answer for A. B is the theory question. Compare the frequency of the waves. Well, remember from the theory we talked about earlier, frequency doesn't change. The frequency is going to stay the same. So watch out for that one. Lambda changes, speed changes, frequency stays the same. Cool beans? All right. Okay, so let's move along to our next question. All right, a student is doing a lab and measures the speed of light to be 2.21 times 10 to the power of 8 meters per second as it travels through a certain substance. So we don't know what it is. Use the table below to determine the identity of the substance. Okay, we have some issues. We are running out of. We don't have a lot of data here, so we've got a list of all these media, but we don't have much. What do we have? What are constants that we have? We got the speed of light in air, and we have the index of refraction in air. So that has been given to us. So, ladies and gentlemen, we have this guy, index of refraction in air. And here we also have the speed of 3 times 10 to the power of 8 meters per second. We have to use the value for air here because we've been given the speed for the other medium, but we don't have the speed for anything else other than air. So that's what we have to use. Okay, so I'm going to scroll down a wee bit so I've got some space to draw. And as always, ladies and gentlemen, draw stuff out so you can see it. Here's our normal line. Here is going to be our surface change, so where we're going from one medium to the other, a medium change. And we are going to have our beam of light that is going to be coming in. So there's our ray of light. And it is going to be bending upwards. Now, if we're going to make this, let's make this water. Let's make this air. Okay, I know that the N, make this 2. Why not? The N of 2 in the air is going to be a value of 1.00. Okay, and we know the speed in air is 3 times 10 to the power of 8 meters per second. Now, when we look at all these other values to pick from, they're all higher than air. So we know that as this ray is going to be coming in, which we are going to try and find this so we can identify what it is. And we have our speed in medium 1, which was given to us to be 2.21 times 10 to the power of 8 meters per second. So we know that if this n is going to be any of these guys, that's v1, is any of these guys, it's going to be higher. That means we're going to be moving from something that is more difficult to move in to something that is going to be easier to move in. So that means this ray of light is going to bend away from the normal as it speeds up. Okay, so we can also look at that here. We'll look at this value here. We're going from here to here. Our speed is speeding up. We can even just see that numerically, even if we don't want to look at the theory there. Okay, so that's how we know that our beam of light here is going to bend towards the normal, or away from the normal, excuse me. Okay, so we have our diagram. And now we need to pick our equation. Well, we have n and v, so my n2 over my n1 is going to equal v1 over v2. So you pick the pieces of the equation that you need. You don't pick all of them. Okay, so I am trying to find my value of n1. So I am going to rearrange my equation, and we are going to multiply out n1. Okay, so my n2 is going to equal v1 n1 over v2. And then I am going to multiply by my v2 over v1. Okay, and then I'm going to wind up with my lovely value of n1 is equal to n2 v2 over v1. Now, another thing you can do, ladies and gentlemen, I don't normally do it because I've never liked this method just because it's me, and I've never liked it right from elementary school, is cross multiplication and division. You can't cross multiply and divide with this equation. Some people love cross multiplying and dividing, and I don't know why. I've never liked it. And weird, but you know this. So what you could do is, if you're trying to find n1, well, we cross multiply here and we divide here, and then your answer will go there. So you are welcome to cross multiply and divide if you want. I've never liked it, but you can go for it if you want. Okay. So I will not deduct marks just because you are choosing to use a method that I've never liked. So we're reasonable about these things. So long as you show your work, make your work legible, we're good. And you're using proper math and physics rules. Okay, so ladies and gentlemen, I'm going to go back to my equation here, plonk my numbers in. So my N2 is 1. My V2 is our 3 times 10 to the power of 8 meters per second. And I am going to divide this by my V1, which is 2.21 times 10 to the power of 8 meters per second. Now, back to unit analysis here, ladies and gentlemen. Notice these 2 meters per second, they cancel. So therefore, we have no units, and we are left with a value of N1 of 1.357 ... And as always, I want your significant digits, please. So 1.36. So now we're going to come up to the table, and hey, looky here. Your substance is going to be ethanol. All right. So, ladies and gentlemen, what do you think? Not too shabby. Okay. All right. So, ladies and gentlemen, what I would like you guys to do now is I want you guys to please pause this video. I want you guys to do some of these practice problems here, and I want you guys to try this. I want you guys to try this particular question on your own before you watch the second half of the video to go over it. I'm going to go over it in the next part of the video with a speed that I'm assuming you've already done the question and are checking your answer. This question is where you're going to be putting your information into a mx plus b scenario, and you're going to need your stat plot. Okay, so we'll take a brief look at the question, and then you're going to pause the video, and then you're going to try it, and you're going to check your answer afterwards. Okay, because you absolutely should be able to do this with all of the y equals mx plus b stuff we've already done. Okay, brief look at the question, then you pause and do that yourself. Okay. So, Aidan sets out to determine the speed of light in a viscous fluid using the principles of refraction. Using a red pen laser, he manipulates the angle of incidence and records the angle of refraction. So here he has the angle, and what you guys are going to do is, making sure your calculator's in degrees, no having a rad time around here, you are going to record your sine of the angles. Okay, and once you've done that, you are going to plot them on the graph. So you guys have the space for this in your notes, and you are going to plot the data on a graph. You are then going to put these pieces of info into your stat plot to get the slope of the graph. It's going to be so much easier to use your stat plot. Don't calculate the slope manual, please use your stat plot. And then once you have finished that, you are going to determine the speed of light in the viscous fluid by taking your equations from Snell's law, setting it up to y equals mx plus b, and then using your slope to solve for the speed. Okay? Okay. So ladies and gentlemen, pause the video, do the question, come back to this. You've paused the video, and you have now come back to the question. Okay, remember, I am going through this, ladies and gentlemen, with the speed that I am assuming you've already done the question. Okay? Okay. So, ladies and gentlemen, your sine of the angles, they should be 0.2588 and 0.4226 and 0.5736 and 0.7071. And the sines of these guys says 0.2079 and 0.3420 and 0.4695 and 0.5878. So, ladies and gentlemen, the fact that you're learning how to do this over video chat and video lesson on YouTube, it's a sign of the times. Yeah, that happened. That happened. Please tell me you're laughing at my jokes. Okay. So, ladies and gentlemen, we have now completed A, and we're going to plot the sine of the angles. Okay. So, ladies and gentlemen, I see you have graph paper. You must be plotting something. All right, so our graphs always need a title. So we're going to have sine of our refracted angle versus the sine of our incident angle. Okay, there's your title. All right, so I'm gonna scroll down so we can see. So, ladies and gentlemen, when you are going to be plotting your graph, you are going to have a point that's going to be our point 2 is going to be around there. And we're going to have a point about a 0.4, get it? 0.4. And then above our about kind of there. And then we're going to be over here. And we'll be about right about there. And then we're going to have, scroll up here. And we're about around there. So you're then going to draw your line of best fit. I am going to attempt this, ladies and gentlemen, but please bear with me. I can't draw a straight line on this thing. I don't know if I have that feature. So it's not going to be a proper line of best fit. You really should be using a ruler. Maybe I have a ruler, or at least a straight edge that I might be able to use. Maybe I can do this. Let's try this. Okay. Bear with me here. Okay, wrong angle of my book. Nope. Okay, you guys get the point. You know how to draw a line of best fit. Ignore the first two. The second, ignore those lines. We tried. I did my best. Yeah, we'll just ignore these. You guys know how to draw a line of best fit. Okay. So, next piece, ladies and gentlemen, once we're finished with me butchering my attempted graph, you are going to go and put these points into your stat plot. Okay, use your graphic calculator. We've done stat plots in class several times. So once you have done that, that's supposed to be an LOT. So using your stat plot, you are going to get your values in your y equals ax plus b. And then you are going to get the value of a, which is the value of your slope, to be 0.8464. And you're going to get the value of b to be negative 0.0133. 0.39. Okay. So, ladies and gentlemen, okay, this guy here is going to be representing air. So the sine of our refracted angle, and this is going to be our fancy medium. Okay, we're going to make air number 1, and we're going to make this medium number 2. All right, so ladies and gentlemen, remember that from your data sheet, the sine of theta 1 over the sine of theta 2 is going to equal my V1 over my V2. Now, ladies and gentlemen, we need to put this into a y equals mxb scenario, so then that way we can get the slope. Now, this guy, the sine of air is my y, and the sine in the medium is going to be my x. So this here is my x, this here is my y. Okay, so when I'm rearranging this, I have to set it up so it's set up to look like y equals mx plus b, so I can use the slope to find the speed in that different medium. Okay, so sine of theta 1 is going to be my y. So I need to get rid of this. I'm going to multiply my sine of theta 2 over. Okay, so that cancels. So sine of theta 1 is my y. And then I have V1 sine of theta 2 divided by V2. Now, just like we did in class before COVID, we would break this down, like break this part up so it looks clearly like y equals mx plus b. Now, this is x. So I am going to just separate these two guys here, so then that way we're multiplying by this guy so it looks more like our x. So sine of theta 1 is equal to V1 over V2 times, we'll put that guy in brackets, my sine of theta 2. So this is my y, ladies and gentlemen. This is my x, and this is going to be, let's try this again. It's Monday. It's not even really Monday. It's Wednesday. That's my m. That is my x. And then plus 0 will be b. Now, when we go and look over here with b, ladies and gentlemen, b is significantly smaller than this guy. So it makes sense theoretically with this setup here. Okay. And also remember, ladies and gentlemen, the data we're using is experimental data. So that means it is going to be off by a bit. Okay. So good old experimental error, source of pain and suffering for scientists everywhere. All right. So, ladies and gentlemen, let's figure out how we can solve for speed in medium 2. How would we do that? We would take our slope. Our slope is going to be a part of V2. So slope is our V1 over V2. Well, do we know the speed of light in air? Of course we do. 3 times 10 to the power of 8. So we have our value of the slope. So our slope from our calculator from your stat plots is 0.864. And then is going to then equal 3 times 10 to the power of 8 divided by V2. Well, we rearrange this guy, and our V2 is 3 times 10 to the power of 8, and we're going to divide that by 0.8464, and you're going to get the lovely value of V2 with your sig digs and units to be 2.54 times 10 to the power of 8 meters per second. Okay, so ladies and gentlemen, let's go back for a moment and think about why we did things a certain way here. Why did I insist that you guys use your calculator and to get your stat plot and not your calculating slope manually? Why did I do that? Once again, source of error. Your calculator is going to be able to plot the graph a lot better than humans can. There's a lot, we've programmed our calculators and made our calculators to be able to do math way better than we can and way more accurately and quickly than we can. So we may as well use the tools that we have available to us in order to do that. So we are reducing our error by using the stat plot, and we're also increasing our consistency and our ability to replicate data. So because if I'm going to calculate slope, depending on how precise I was with my points, plotting them on the graph. And as you can see, we had a mess with my line of best fit. It's going to change the data from when I do it to when you do it to when your friend does calculating slope on a piece of paper. Whereas if we put it in a stat plot, we're all going to get the same answer. Assuming we're all using the same calculators and they're working properly. All right. So ladies and gentlemen, that's it for this particular video. So go to some practice problems, become comfortable with this stuff before we go and start looking at critical angles. All right. Ladies and gentlemen, no fires, injuries, or explosions.